In a 120/208 volt 4-wire electrical system, understanding how to calculate the neutral current when dealing with harmonic loads is essential for ensuring safety and preventing overloading. When dealing with a balanced three-phase harmonic load, the current in the neutral conductor is not simply the arithmetic sum of the phase currents. Instead, it's calculated using a specific formula that takes into account the harmonic components. The fundamental equation for determining the neutral current, denoted as N, is given by N equals the square root of 3 times I, where I represents the current in each phase due to the harmonic load. The square root of 3 is approximately 1.732. Now, let's consider a scenario where each phase of a 120/208 volt system carries a harmonic load of 1000 amps. To find the neutral current, we substitute this value into the formula. So, N equals the square root of 3 times 1000 amps. Performing this calculation, we find that N equals 1.732 times 1000 amps, which equals 1732 amps. Therefore, with a 1000 amp harmonic load on each phase, the neutral conductor carries a current of 1732 amps. It is crucial to remember that this calculation is based on the assumption of a balanced harmonic load. In practical scenarios, loads may not always be perfectly balanced, which can lead to variations in the neutral current. In such cases, more complex methods of analysis might be required to accurately determine the neutral current. When dealing with harmonic loads, several factors can affect the neutral current. Firstly, the magnitude of the harmonic current significantly impacts the neutral current. Higher harmonic currents result in a higher neutral current. Secondly, the phase angle between the harmonic currents in each phase also plays a role. If the harmonic currents are perfectly in phase, the neutral current will be at its maximum. Thirdly, the presence of tripling harmonics, which are odd multiples of the third harmonic, such as the third, ninth, and 50th harmonics, are particularly significant because they add directly in the neutral conductor. Therefore, the higher the proportion of tripling harmonics, the greater the neutral current. To mitigate the effects of harmonic currents on the neutral conductor, several measures can be taken. Firstly, using harmonic filters to reduce the magnitude of harmonic currents is an effective approach. Harmonic filters are designed to block or divert specific harmonic frequencies, preventing them from flowing through the system. Secondly, balancing the loads across the 3 phases can help minimize the neutral current. By ensuring that each phase carries a similar amount of load, the harmonic currents tend to cancel each other out in the neutral conductor. Thirdly, using oversized neutral conductors can provide additional capacity to handle the increased current due to harmonic loads. This ensures that the neutral conductor does not overheat or become overloaded. Fourthly, employing phase cancellation techniques, such as using delta-Y transformers, can help reduce the amount of tripling harmonics in the system. Delta-Y transformers block the flow of tripling harmonics from the delta side to the Y side, preventing them from reaching the neutral conductor. In summary, when dealing with balanced 3-phase harmonic loads, the neutral current can be calculated using the formula N equals the square root of 3 times I. However, it's essential to consider the factors that can affect the neutral current, such as the magnitude of harmonic currents, the phase angle between them, and the presence of tripling harmonics. By implementing appropriate mitigation measures, such as using harmonic filters, balancing loads, using oversized neutral conductors, and employing phase cancellation techniques, the effects of harmonic currents on the neutral conductor can be minimized. These measures help ensure the safe and reliable operation of the electrical system. In addition to the previous discussion, it is important to consider the impact of nonlinear loads on the harmonic content of the electrical system. Nonlinear loads, such as electronic devices, computers, and variable frequency drives, draw current in a non-sinusoidal manner, which introduces harmonic currents into the system. These harmonic currents can cause various problems, including increased neutral current, overheating of transformers and conductors, voltage distortion, and malfunction of sensitive equipment. Therefore, it is essential to identify and address the sources of harmonic currents in the electrical system. One way to identify harmonic sources is to perform a harmonic analysis using specialized equipment such as a harmonic analyzer. A harmonic analyzer measures the magnitude and phase angle of the different harmonic frequencies present in the current and voltage waveforms. This information can be used to pinpoint the sources of harmonic currents and assess the severity of the harmonic distortion. Once the harmonic sources have been identified, appropriate mitigation measures can be implemented. In addition to the measures already mentioned, such as harmonic filters and load balancing, other techniques can be used to reduce harmonic distortion. One such technique is the use of active harmonic filters. Active harmonic filters are electronic devices that inject compensating currents into the system to cancel out the harmonic currents produced by nonlinear loads. Unlike passive harmonic filters, which are tuned to specific harmonic frequencies, active harmonic filters can adapt to changing load conditions and provide more effective harmonic mitigation. Another technique is the use of harmonic reducing transformers. These transformers are designed to minimize the generation of harmonic currents by using special core materials and winding configurations. Harmonic reducing transformers can be particularly effective in reducing the amount of tripling harmonics in the system. In addition to technical solutions, proper design and installation practices can also help minimize harmonic distortion. For example, using shielded cables and grounding conductors can reduce the amount of electromagnetic interference caused by harmonic currents. Also, separating sensitive equipment from harmonic-producing loads can prevent malfunctions and ensure reliable operation. It is also important to consider the relevant standards and regulations regarding harmonic distortion. Many countries and regions have established limits on the amount of harmonic distortion that is allowed in electrical systems. These limits are typically specified in terms of total harmonic distortion or individual harmonic distortion levels. Compliance with these standards is essential for ensuring the safe and reliable operation of the electrical system. To summarize, dealing with harmonic loads requires a comprehensive approach that includes identifying harmonic sources, implementing appropriate mitigation measures, and complying with relevant standards and regulations. By addressing these issues, the negative effects of harmonic currents can be minimized and the electrical system can operate safely and reliably. Furthermore, it is crucial to understand the implications of an overloaded neutral conductor due to harmonic currents. An overloaded neutral can lead to several serious consequences, including overheating, insulation breakdown, and even fire hazards. When the neutral conductor is overloaded, the excessive current flow generates heat, which can damage the conductor's insulation and surrounding materials. Over time, this can lead to insulation breakdown, creating a risk of short circuits and ground faults. In addition, an overloaded neutral can cause voltage imbalances in the system, which can affect the performance of sensitive equipment and lead to malfunctions. Therefore, it is essential to ensure that the neutral conductor is adequately sized to handle the expected harmonic currents. The National Electrical Code, or NEC, provides guidelines for sizing neutral conductors in systems with harmonic loads. NEC Section 220.61 specifies the requirements for calculating the neutral load in a 3-wire circuit consisting of 2-phase wires and a neutral wire. According to NEC Section 220.61, the neutral conductor must be sized to carry the maximum unbalanced load between the phase wires and the neutral. In addition, NEC Section 220.61 requires that the neutral conductor be sized to carry the maximum current of any single phase plus the sum of the harmonic currents that are present in the neutral conductor. To determine the appropriate size of the neutral conductor, it is necessary to calculate the harmonic currents that are expected to flow in the neutral. This can be done using a harmonic analysis tool or by applying the formula N equals the square root of 3 times I, as previously discussed. Once the harmonic currents have been calculated, the neutral conductor can be sized according to the requirements of NEC Section 220.61. In some cases, it may be necessary to increase the size of the neutral conductor beyond the minimum required by NEC Section 220.61 to ensure that it can handle the expected harmonic currents without overheating or becoming overloaded. This is particularly important in systems with a high proportion of nonlinear loads. In addition to proper sizing, It is also important to ensure that the neutral conductor is properly installed and maintained. The neutral conductor must be securely connected to the neutral busbar, and all other neutral connections must be tight and free of corrosion. Regular inspections should be conducted to check for signs of overheating or insulation damage. If any problems are found, they should be addressed immediately to prevent potential hazards. In conclusion, an overloaded neutral conductor can pose serious risks to the safety and reliability of an electrical system. Therefore, it is essential to understand the implications of harmonic currents and to ensure that the neutral conductor is properly sized, installed, and maintained. By following the guidelines of the National Electrical Code and implementing appropriate mitigation measures, the risks associated with harmonic currents can be minimized and the electrical system can operate safely and reliably. When selecting conductors for the neutral, several factors should be taken into consideration, including the ampacity of the conductor, the insulation type, and the environmental conditions. The ampacity of the conductor refers to its current carrying capacity, which is determined by its size and material. The ampacity must be sufficient to handle the expected harmonic currents without overheating or becoming overloaded. The insulation type of the conductor affects its ability to withstand high temperatures and resist degradation from environmental factors such as moisture and chemicals. The insulation type should be selected based on the specific application and the environmental conditions to which the conductor will be exposed. In addition to the conductor itself, the overcurrent protection devices, such as circuit breakers and fuses, must also be properly selected and sized to protect the neutral conductor from overloads and short circuits. The overcurrent protection devices should be rated to interrupt the maximum fault current that is expected to flow in the neutral conductor. It is also important to consider the voltage drop in the neutral conductor. Voltage drop occurs when the current flowing through the conductor causes a reduction in voltage at the load end. Excessive voltage drop can affect the performance of sensitive equipment and lead to malfunctions. To minimize voltage drop, the neutral conductor should be sized appropriately and installed in a manner that minimizes its length and resistance. Furthermore, grounding is a critical aspect of electrical safety and plays a vital role in mitigating the effects of harmonic currents. Proper grounding provides a low impedance path for fault currents to flow back to the source, which helps to quickly clear faults and prevent electrical shock hazards. In systems with harmonic loads, it is particularly important to ensure that the grounding system is properly designed and installed to handle the increased harmonic currents. The grounding system should include a grounding electrode system, a grounding electrode conductor, and equipment grounding conductors. The grounding electrode system provides a connection to the earth which helps to stabilize the voltage and provide a reference point for the electrical system. The grounding electrode conductor connects the grounding electrode system to the neutral busbar in the service equipment. Equipment grounding conductors provide a low impedance path for fault currents to flow from electrical equipment back to the source. In addition to the basic grounding requirements, it is also important to consider the use of supplemental grounding electrodes in systems with harmonic loads. Supplemental grounding electrodes can help to reduce the impedance of the grounding system and improve its ability to handle harmonic currents. When installing grounding electrodes, it is important to follow the requirements of the National Electrical Code. The NEC specifies the types of grounding electrodes that are permitted, the minimum size of the grounding electrode conductor, and the methods for installing grounding electrodes. By following the NEC requirements, the grounding system can be ensured to be safe and effective. In summary, selecting the appropriate conductors and overcurrent protection devices, minimizing voltage drop, and providing proper grounding are all essential aspects of dealing with harmonic loads in electrical systems. By addressing these issues, the risks associated with harmonic currents can be minimized, and the electrical system can operate safely and reliably. Additionally, it's important to consider the impact of harmonic currents on transformers. Transformers are susceptible to overheating and reduced lifespan when subjected to harmonic currents. The increased current flow due to harmonics causes additional losses in the transformer core and windings, leading to higher operating temperatures. These elevated temperatures can degrade the transformer's insulation and reduce its overall lifespan. To mitigate the effects of harmonic currents on transformers, several strategies can be employed. Firstly, directing the transformer's capacity can help to reduce the stress on the transformer and prevent overheating. Directing involves reducing the transformer's rated kVA capacity to account for the harmonic content of the load. The amount of directing depends on the severity of the harmonic distortion. Secondly, using K-rated transformers can provide enhanced performance in harmonic-rich environments. K-rated transformers are specifically designed to withstand the effects of harmonic currents and minimize overheating. They typically feature larger conductors, improved core designs, and enhanced insulation systems. Thirdly, harmonic filters can be installed to reduce the harmonic currents flowing through the transformer. Harmonic filters can be either passive or active, and they are designed to block or divert specific harmonic frequencies. In addition to these strategies, regular monitoring of the transformer's operating temperature can help to identify potential problems early on. Thermal monitoring devices can be installed to continuously measure the transformer's temperature and provide an alarm if the temperature exceeds a predetermined limit. This allows for timely intervention to prevent overheating and potential damage to the transformer. Furthermore, it is important to consider the impact of harmonic currents on power factor. Power factor is a measure of how effectively electrical power is being used. Harmonic currents can distort the current waveform and reduce the power factor, leading to increased energy consumption and higher utility bills. To improve the power factor in systems with harmonic loads, power factor correction capacitors can be installed. Power factor correction capacitors provide reactive power to offset the reactive power caused by inductive loads, thereby improving the power factor. However, it is important to know that power factor correction capacitors can also amplify harmonic currents if not properly selected and installed. Therefore, it is essential to perform a harmonic analysis before installing power factor correction capacitors to ensure that they will not exacerbate the harmonic distortion problem. In conclusion, harmonic currents can have a significant impact on electrical systems, affecting transformers, power factor, and overall system performance. By understanding the effects of harmonic currents and implementing appropriate mitigation strategies, the risks associated with harmonic distortion can be minimized, and the electrical system can operate efficiently and reliably. Harmonic mitigation is not a one-size-fits-all solution. The best approach depends on the specific characteristics of the electrical system, the nature of the harmonic loads, and the desired level of performance. It is important to consult with qualified electrical engineers to develop a comprehensive harmonic mitigation plan that is tailored to the specific needs of the system. Regular monitoring and maintenance are also essential to ensure that the harmonic mitigation measures continue to be effective over time. By taking a proactive approach to harmonic mitigation, the long-term reliability and efficiency of the electrical system can be enhanced. In addition to the previously mentioned methods of mitigating harmonic currents, another approach is to use adjustable speed drives, also known as variable frequency drives or VFD, with active front-end rectifiers. Traditional VFD use diode bridge rectifiers, which are a significant source of harmonic currents. Active front-end rectifiers, on the other hand, use insulated gate bipolar transistors, or IGBTs, to actively shape the input current waveform and reduce harmonic distortion. VFD with active front-end rectifiers can significantly reduce harmonic currents compared to traditional VFD. They also offer other benefits, such as improved power factor and reduced voltage distortion. However, they are typically more expensive than traditional VFD. Therefore, the decision to use VFD with active front-end rectifiers should be based on a cost-benefit analysis that takes into account the specific needs of the application. Another important consideration when dealing with harmonic currents is the impact on metering equipment. Harmonic currents can affect the accuracy of metering equipment, leading to inaccurate billing and potential disputes with the utility company. Traditional electromechanical meters are particularly susceptible to errors caused by harmonic currents. Electronic meters are generally more accurate than electromechanical meters, but they can still be affected by harmonic currents if not properly designed. To ensure accurate metering in systems with harmonic loads, it is important to use metering equipment that is designed to accurately measure non-sinusoidal waveforms. These meters typically use advanced signal processing techniques to filter out harmonic currents and provide an accurate reading of the fundamental frequency. It is also important to periodically calibrate metering equipment to ensure that it is operating within its specified accuracy range. In addition to the technical aspects of harmonic mitigation, it is also important to consider the economic aspect. Harmonic mitigation measures can be costly to implement, but they can also provide significant cost savings in the long run. By reducing harmonic distortion, energy consumption can be reduced, equipment lifespan can be extended, and the risk of equipment failure can be minimized. These cost savings can often offset the initial investment in harmonic mitigation measures. Therefore, it is important to perform a thorough cost-benefit analysis before implementing any harmonic mitigation measures. The cost-benefit analysis should take into account the initial investment, the expected cost savings, and the potential risks of not mitigating harmonic distortion. In conclusion, dealing with harmonic currents requires a multifaceted approach that includes understanding the causes and effects of harmonic distortion, implementing appropriate mitigation measures, and considering the technical and economic aspects of harmonic mitigation. By taking a proactive approach to harmonic mitigation, the risks associated with harmonic currents can be minimized, and the electrical system can operate efficiently, reliably, and safely.